maybe you don't. Start with the ones that you definitely can do, or the simplest ones. Like eliminate things early that you can eliminate. So when you look at this, which one strikes you as maybe the simplest one to deal with?
C.
How about C? There's again, hard, difficult. That's all relative, right? But maybe C. What is not in that?
X.
There's no x in it, so it's independent of x, meaning it's only going to exist on the zy plane and then get scaled forward and backward on the x-axis. So which one is like that? Oh, there it is, right? So we know that one's C. Absolutely. So we did that one. What's the next one that maybe looks a little bit nice?
Do the absolute value.
Let's do the absolute. Hold on. Let's just knock off the ones that are kind of singletons. H. Let's look at H. G is another one, absolutely. But let's look at H here. Well, Z equals it isn't, but it's the product of x and y, and it's always going to be what? So it's always going to be positive. So you can look at these and eliminate some of them, like the first one, right? The fourth one. Also, like you could plot some points if you wanted to.
Yeah. Also when.
Also what?
When x or y is 0, then z is 1.
Then z is there. So this thing hugs the x, and there's infinite gravity to the x and y axes, right? So which one does that match for?
3.
Kind of looks for 3, right? Yeah. Kind of looks for 3. And the other thing is, when you have two things multiply, yeah, it looks like it's going to be straighter. It's going to be bigger. As x and y both get bigger, that's where it's biggest, right? And these points happen when x and y are both the furthest from the origin. So we think that one's what? H right there. I like that. Good. So which one do you want to target next? What's the good? G?
Yeah, G's pretty cool.
That's the only one that, well, it has, it's
Actually, I like A.
You want to do A?
I like A.
You like A more?
I'm so proud of myself.
Okay. So Henry, tell me about A. What do you note about A?
So basically, I noticed. Okay, so I kind of rewrote it a little.
Yep.
I did it as x of y over e to the x squared plus y squared plus blah blah blah.
Oh, you got rid of the negative exponent?
Yeah. Just
Okay,
kind of
that's fine. So z is equal to xy over e to the. Exactly right. Okay.
And then I thought about it in terms of limits.
Yeah. Okay.
Because as x and y
Yep.
get bigger,
Yep.
it's going to get smaller.
It's going to get smaller because e to the x squared plus y squared gets bigger a lot faster than xy.
Exactly. So that's what I thought.
So you know it's going to. So as x and y get really big, it's going to go to 0 from no matter which side of the axis. Also, when x or y is 0, what do you know?
0.
It's 0. Exactly right.
And also the last thing is that
What else? Yeah.
when x and y are either both negative or both positive,
Yep.
then it's going to start from really big and then go down closer and closer to 0. But
So that's a great observation, because then what does it immediately go to? That right there narrows it down to one of them. 4. It immediately goes to 4 because you have these two humps in them. You also know it's not going to go berserk like that. It's not going to go, you can't really see this, but it's not going to go berserk like that one because there's nothing in it that dictates repetitive peaks.
Yeah.
It's going to peak up in both x positive and y positive, absolutely, for a little while they're less than 1, right? And then it's going to go straight down again. But when they are opposite signed, it's not going to happen. Why isn't it going to happen when they're opposite signed?
Because
They make sense.
or they
Positive.
positive. Yeah, because negative times negative is positive. Positive times
So you have, okay, so that means the numerator is going to be,
positive.
no, I'm saying if they're opposite signs. So if x and y are both opposite signs.
Opposite signs, then the numerator is going to be negative.
Okay, so what? So then keep going with that. So if the
And because on the in the denominator they're both squared, so the sign never changes on the denominator, so nothing happened there.
so you have negative over positive.
Yeah.
So it's going to be negative. So I guess my question is, why isn't there a peak then? Why isn't there like a negative peak? Like, so when we're looking at this one right here.
There is a negative.
Oh, it is there. I didn't see it. I didn't zoom in far enough. Yes. Excellent. Sorry, I was like, there should be. Okay, there it is. I just have to zoom in. So hold on, let me get this down. So we know that this one, 4 correlates to which one? A, right?
Yeah.
Okay, good. We're cruising along here. Nice. Okay. So let's call this one. So D, the yellow one. It's always going to be what? It's always going to be below the XY plane. So it's going to go down, right? And there's only one that's below the entire time. Which one is that? The first one. So this right here is what, D? Nice. Cool. And you also know there's going to be some sort of like rotational symmetry because you have an x squared plus y squared. Or y, or both x and y equals 0. What happens?
0.
Well, if you put both in.
Oh, I'm sorry. If you plug, I'm sorry. It changes, doesn't
Yes,
it?
8.
It has to be 8 right there. So no, this one is going to be E. And then you're left with which ones here? What are we left with? Which ones haven't we done?
F and I.
F and I. F and I.
5 and 2.
Correct. So how do we want to go about figuring? So you take what you get and you work at it. It's hard. It's hard. What it's asking you for is find a plane so that when it intersects this thing, you get a parabola, then a sine curve, then a straight line. Okay? The planes we're going to work with are just, and it tells you what to work with. X, Y, or Z equals a constant. So I'll just throw one of those out there, for example. Let's say we ended up with, I don't know, Y is equal to 0. Is that a plane?
Yes.
When you look for the intersection of two things, you can do the substitution, right? What do you plug in for Y? You plug in 0. So what do you end up with? Z is equal to x squared plus 1 sine of what?
0.
0 plus.
0.
So what do you end up with?
0.
That's a plane. Is that any of the three we wanted?
Yeah.
No. Is it? Is it? No, it's not. Does it ask for a plane? But that's what we're doing. We're testing out values for x, y, or z and seeing if we can generate each of these things. Now, to get a parabola, what's the only thing in here that can have a parabolic shape? There's two things. The x squared or the y squared. Okay, so if we just want the y squared to be there, if we just wanted the y squared to be there, we'd have to get rid of this thing. Is there anything we can plug in for x that gets rid of it?
No.
No. So what's the only other thing that has a parabolic structure? The x squared. So give me a value for y. Pick anybody. Pick any value. How about y is equal to, I don't know, how about the square root of 17? Why not? Why not, you ask? Well, how about this? What happens? You get z is equal to x squared plus 1 times sine of what? 17 plus 17x. Is that a parabola? It is. Why not? That is a parabola. Can you write that in standard form? Yes. You're going to end up with sine of the square root of 17 x squared plus 17x plus sine the square root of 17. Is that a parabola?
Yes.
Yeah. It's y equals any constant other than 0. There's your set. I mean, we could expand this question to what's the maximal set? The maximal set here is any number other y equals not 0. Okay. So that's, yeah, what's your question?
My question is, how do I get
What you said for the third one was you want sine y to be 0, right? But y should not be 0.
Not saying like y is pi.
Exactly. So if y is pi, you end up with z is equal to x squared plus 1 times sine of pi plus what? Pi squared x, right? So if you do that out, you end up with z squared is equal to what? Well, z is equal to pi squared x. Z equals x. What is that? It's a line. Yeah, that's right. Exactly. Very good. The set of all points that are equidistant from the x-axis and z, right? So if you have two axes here, or three, excuse me. Yeah, it is hard to draw. X, y, and z, right? So if let's just look at the x, y plane. If you just look at the xy plane, so you're doing like a cross section at the xy plane, what are the set of points that are equidistant from the xy axis and the zy plane?
Wait, ZY or X?
It was the x-axis and the yz plane. The x-axis and the yz and the yz plane. That's actually going to be this set of points, like this. And what about? Oh, then there's also these points right here. Sorry, excuse me. There's these points right there, right?
Oh, yeah.
But then you can spin it. You can spin it around. So what does this actually look like? So it's rather hard to draw. Well, I am an infinite number of them. So what do you end up with? You have this cylinder on the back, and it all comes together right there. It's hard. It's really hard to draw. Yeah, like that. If you looked at it from above, it would look like an X. Yeah, it's just something neat. There are other conclusions you can make in terms of what happens as the temperature goes up or down, that kind of thing. So if, for example, rainfall remains static right here, let's say you have this right here, the static, what would the optimal temperature be when the rainfall is there? What would it be? Like 74. Exactly, right? But let's say the rainfall was, I don't know, here instead. Where do you want it to be? Either what? Oh no, you want it to be, oh, it's still 74. Oh, okay, cool. So I'd have to change it a little bit. But the point is, you can have different analyses when we have different tools. Like, we're going to look at things like what happens as you change it in a non-axial, like parallel to the axis. That kind of thing. Three-dimensional set of data, 2D flattening. I could give you this drawing and not give you this and say, please generate for me this contour diagram. How would you go generating that contour diagram? Collapse all of your level curves, exactly. How can you do it mathematically in a more accurate sense? Well, you have z is equal to x squared plus y squared. Each of these slices, like this slice right there, you see that slice I'm trying to draw right there? That slice is z equals some constant, right? So for example, let's let one z equals, I don't know, 2. What does 2 equal x squared plus y squared? What is that? Circle with radius, root 2, right? So what do you end up with? You end up with circles. That's how you can prove all of the level curves are circles, because you're setting your z value to a constant and then another constant and then another constant. It's key though. What do you see here? What are these numbers that I'm circling? Those are the, well, no, it's not the radius. That's the output value, right? That's the z value right there. So on this path right here, what is the z value on this path?
R2.
Exactly. Exactly. What's the radius?
Square root 2.
Square root of 2. And that is a terrible time to use the highlighter. Okay. Root 2. There you go. Okay. What is this? It's a plane, right? So what do level curves look like for a plane? Lots of lines. So when you do a plane, you're going to get something that looks like this. The steepness is going to, but they all should be parallel, right? They all should be parallel. If you're looking straight down on a plane, you're going to see parallel level curves. Exactly.